Good evening, everybody. I know it's been a while since we've done any game development and I apologize for that. So let's get right into our next stage of our game, which is going to be adding some collision detection. Now, the kind of collision detection we're going to add is based around bounding boxes. This is one of the easiest ones to implement, so it's a good place to start with, but kind of has some downsides. And one of the downsides is that the collision area might not exactly match the sprite. So in this case we've got Mario and his collision box, and if we've got a collision that's kind of right on the edge here, that will register as a collision even though none of his actual pixels are touching. But for simple games, especially ones that are relatively fast moving, the effect is still pretty good, as you'll see. So what we're going to do here is first, unfortunately, we're going to make some infrastructure, and we're going to do that in a new folder called maths. And we are going to create a class that represents our new bounding box. And it's going to be a public class, of course. And we are going to define our bounding box by two coordinates, one at the top left and one at the bottom right, both of which together will define our rectangle. So let's name them perhaps something sensible like top left and bottom right. That seems pretty reasonable to me. Yeah, let's move those up here perhaps. So that's enough to represent our bounding box, but the interesting thing is we want to check if a bounding box collides with another one. So we'll do something like bounding box is colliding with and the other box. So we want to return true if is colliding with the other, false otherwise. So how we're going to implement our is colliding with function is we're going to check that these four cases where they're not colliding is false, basically. So we know that if this is in the middle and the other is way off to the left, then it's not colliding, and we can see that occurs when the top left x of this is greater than the bottom right x of other. You can see on increasing x is this way, increasing y is that way. So that means if it's to the right, it's bigger. So it's pretty easy to write that rule, because if they're not bigger, they have to be less than or equal to be colliding. So that means we could go return this dot top left dot x. That guy there has to be less than or equal to other dot bottom right dot x. So that takes care of that case there. Similarly on this one, we want this dot y1 to be overlapping with other dot y2, the one on the bottom right. So we go and this dot top left dot y, that guy there, is overlapping with other dot bottom right dot y. Other dot bottom right dot y, which takes care of this one. Now this case is actually the same as this case here, except you could imagine that this and other is just swapped around, because instead of being to the left, the other is to the right. So that means that we can just take this row here and go other dot top left dot x is less than or equal to this dot bottom right dot x. So that means that this and this must be overlapping, which takes care of this case. This bottom case here is the same as the top case, except this and this are, this and other is flipped around. So that means that we can just do the same as this one, except other dot top left dot y is less than or equal to this dot bottom right dot y. And if all of those are true, that means that none of these cases are happening, so they must be overlapping either like this, or like this, or like this, or like this, or perhaps even completely inside of each other. So that's a good start, but in addition to that, when the objects actually collide, so let's go back to our two Marios, say they collide like that. Oops, let's cut that a little bit finer. Let's say that when they step inside of each other like that. We also need to know which way these Marios should be moved so they're not inside of each other again. For example, if they collide and they step just a little bit like that, we don't want the next frame of the animation to move this guy up here. We actually want him to move towards the ledge where he's penetrated inside the least. So if he was inside a tiny bit like that, we'd expect him to move to there. If he was inside a little bit from the bottom edge, we'd expect him to move out to the bottom edge there. So that means when he collides on the bottom, he'll move something like this and not suddenly pop up to the opposite end. So that means we need a function which returns a vector telling us which direction he should be moved to, and we're going to call that, what should we call that? Let's call that penetration test. So the way that we're going to do that is we're going to measure the penetration distance of all four edges. So left penetration amount. Oops, what happened to our, do we have our system imported? There we go. This dot top left dot x subtract other dot bottom right dot x. So top left dot x subtract the bottom right dot x is how much he would be penetrated onto the left edge, top left to bottom right penetration, and the right edge is going to be the opposite. We're going to subtract the top left of this one from the bottom right of that one, because they would be penetrated in like that. So we would go the other one's top left, take this one's bottom right, So top penetration, that's going to be fairly similar. It's going to be this one's top left y, subtract this one's bottom right dot y. Top left dot y, subtract top left dot y, select other dot bottom right dot y. Does that make sense? I think it does. Top left and the bottom, remember y gets bigger going downwards. So if that one is overlapping with the bottom one, yep, all good. And now finally our bottom penetration amount is just going to be the opposite of our top penetration amount. There we go, so that ends up with a nice symmetry where it goes this other, this other. Now we want to select the minimum of all of these because we are interested in which edge we penetrated into the least. To make that easier, I'm going to put those all into an array. And what we are going to do is select the minimum one out of that array. Whoops, that's not quite right. We actually wanted to use the link function minimum. Will it import that for us? Yes, it will. Determine how much we penetrated into each edge. Get the edge we penetrated into the least. Now finally we want to convert that into a vector so that if our object is penetrating in, we can just add that vector to the object we want to move, and rather than being inside each other, they'll just be touching. So if minimum equals our left penetration amount, we want to return a vector that moves to the left. Else, if our minimum is right penetration amount, we want to return a new vector which returns to the right. Else, if our minimum is our top penetration amount, we want to return a new vector 2 which moves to the top. And that means our last possible case is if we've got a vector on the bottom, then we want to return our new vector that moves things downwards. Oops, there we go. Let's see if that builds. So that's all of the infrastructure that we need for our bounding box collision. On our next video, what we're going to do is use these functions from the world class and react to the collisions that this bounding box class detects. So tune in next time for that, and have a good one.